Assalamu alaikum and hello everyone. I welcome you all in today's webinar on preliminary geophysical investigations and technologies in construction industry. The resource person for today's webinar is Dr. Fahimullah. He is a senior geophysicist with Masters and MPhil from Quaid-e-Azam University, Islamabad, Pakistan, and he received his PhD from University of Chinese Academy of Sciences. He has 6 years of research and practical experience in near surface engineering geophysics, methods for hazard evaluation and assessment. He is currently working as a senior geophysicist in Future Expert Geophysics, which is a Saudi Arabia based geophysical investigations company. Without any further delay, I would like to invite Dr. Fahimullah to start his webinar. Thank you so much.
Thank you. We are using in construction industry before doing construction, we need to know the subsurface conditions. We know to different ground conditions according to the structure. And mostly you will understand what type of method we are using and how these methods are actually applicable in this industry. So without wasting our time, let's start. Yeah. So geophysical investigation has become essential for major civil project due to its importance. The data obtained on the subsurface space with a reasonable time and cost. And actually, the most important thing are the instrument, because these instruments are really like patent instruments and novel methodology they use to understand the subsurface conditions, and they are actually helpful or they back actually the geotechnical drilling program. Like for example, you cannot drill a lot of boreholes in some site. So to understand the overall scenario of the earth, you can perform geophysical investigations. There are a number of methods. You will further know about them based on the conditions of the ground, which methods we apply. And then you can actually correlate all these methods with the geophysical result, and then you can interpret the subsurface conditions. So here I will explain why we need these applications like geophysical methods and what are their applications in the construction industry. Like first of all, in some site, if there are any cavities, voids, and sinkholes, so we can detect by using these methods. Also, underground utilities, cable pipes, we can detect. For example, if in an area we need to understand the depth of a bedrock, or we can say overburden thickness. For example, in some projects, they need to know the overburden thickness, so they can estimate the cost of the removal of those burdens. So geophysical investigation can actually provide these results. Also, weak zones, like for some mega projects or construction buildings, we need to understand the subsurface weak zones. Also, soil rock dynamic properties, we can understand from them. Look at, and the other are some of the environmental projects, like we can understand the where the buried waste is actually buried, and like monitoring the changes in groundwater or contaminations, measuring of VS30. This is a very known phenomena to you guys, like average of the shear velocity to 30 meter. We actually estimate the 30 meter shear velocity, and then the result we provide to the client. So detection of archaeological, these are like in mining industry, also in groundwater investigation, and the overburden geological. So in summary, I have divided all these in 3 aspects. The first is surface geophysics, the second is borehole geophysics, and third is marine geophysics. So in surface geophysics, we apply a number of methods on surface. On the surface, we apply these methods. Either they may be in 2-dimensional or in 3-dimensional, and then we understand the subsurface conditions. So some of them may be known to you, like electrical resistivity methods, surface seismic methods, ground penetrating radars, microgravity, electromagnetic methods. So in every method, there are different they are subdivided into different uh, methods. And the borehole geophysics, like for example, if drills are being done, and for those drills, we need to understand the conditions of those boreholes and the lithology involved in those boreholes. Then we need to perform some additional tests as well, like seismic borehole seismic surveys. There may be a number of seismic borehole surveys, like standard cross hole, down hole, etc. Borehole seismic tomography survey. These are actually, if you know about borehole geophysics, these are somehow similar, but the methods and the instruments are different. Simple borehole geophysical logging. This is now another aspect of logging in order to. This actually tells us about the quantitative and qualitative properties of the soils and rocks inside that boreholes. So, and the third is marine geophysics. In marine geophysics, we also apply the similar methods in order to understand the depth of the bedrock, also the urban research. So we will further study about this, and let us learn how we actually apply these methods and what can be the result of these methods. So these methods apply to all aspects of engineering geophysics. Either they can be on onshore as well as offshore. So the first is surface geophysical survey. I will start with. The next will be borehole geophysics survey, and third I will discuss marine geophysical survey. So in surface geophysical survey, you can see that in seismic methods, there are seismic methods, electrical methods, ground penetrating radars, microgravity, magnetic methods, and vibration methods. The target in some aspect, like for example, in seismic and electrical, sometime the target is same, but we apply different methods based on the ground conditions. For example, somewhere the ground conditions will be really hard and we cannot apply seismic, then we choose electrical methods. Similarly, in some conditions, the like ground penetrating radar is like the target based. For example, if the client says that we just need to know the buried pipes in 2-3 meters, then we apply ground penetrating radar. Simple microgravity is mostly used for mining purposes, like mineral exploration and mining. But here also in construction industry, they have some role in detecting like big cavities or large sinkholes. Same magnetometer is also mostly used in mining industry, but still somehow we can use them in geotechnical industry as well. And vibration monitoring is a passive method. We will also discuss about that. So, sir, the second is the borehole geophysics survey. So in borehole geophysics survey, there are a number of seismic surveys like PS logging. From the name, we can suggest that we need to know the P wave and S wave velocity in the borehole to understand, because every rock has a specific P wave and a specific S wave. So based on those P and S wave, we can actually differentiate different lithologies. And similarly, these are other methods: full sonic waves and standard cross hole method, parallel seismic. So all we will discuss these methods. The second part is related to logging. Logging is a little bit different than borehole seismic survey, because in logging we actually we are more interested in the for example, the density or the porosity of some lithologies. So that's why we apply these logging methods, which are actually different than the borehole seismic surveys. And the third is marine geophysics. In marine geophysical survey, we will discuss like single and multi-beam echo sounding surveys, marine sub-bottom profiling, side scan, sonar survey, and marine magnetic surveys. So let's start with the surface geophysical survey. The first is like in seismic, the seismic method which we apply on some site in order to understand the subsurface conditions. Like they can be divided into three parts. The first will be seismic refraction, seismic surface waves, and seismic reflection method. Now from this picture, you can see that whenever if a seismic source is applied to an earth, so it produces some waves like acoustic waves, and these waves can be differentiated, or based on these three types of waves, actually these three methods are derived. The first wave, which directly actually goes to the receiver, we can say surface wave methods, and these methods are mostly like multi-channel analysis of surface waves methods. And the next is if some wave is directly reflected and received to the receiver, then we can actually categorize this as a reflection method. And somehow when the reflected method, when it's reflected with some angle, pass through another medium and then refracted back, then we can say that this is. So the function of the application of all these three methods, further I will explain how we actually do, or how we actually apply these methods based on our targets. So in surface view method, the steps are simple. First, we apply the, for example, we arrange some receivers, and then we apply the our source, and then we gather the data. The data is in this shape, like in section form. And then we do some dispersion analysis. In dispersion analysis, we pick the desired energies. Either it must be in phase velocity, or it must be in frequency domains. And after doing all these, the third step is then we generate layer models. The layer models is actually a very old geo algorithm based layer modeling. When we convert all our acquired data to this layer model, then we develop one section. And in this sections, in step 4, the 2D sections, you can see that it actually tells us the different layer of the earth. The upper layer, the middle layer, it is actually divided into 3 layers. So these are the basic like process of seismic surface waves methods. And the applications, why actually we are doing this. So the first application, if you can see that we are actually trying to determine the depth and thickness of a stratigraphic layer. For example, here in this section, the depth rock is below 6 meters. And if we apply this method to a really big profile, like for example, 2-kilometer profile, then we will understand the character or the nature of the bedrock in that area. And the upper surface, like we can say that the upper surface is like 6 meters soft. And similarly, we can compare all these with our borehole data acquired. And for example, this is our borehole. When we come, this is our borehole at point 40, and it is just 1 point measurement. But from 0 to 80 meter, we can see that we have acquired all the data, and then just comparing with one borehole, we don't need any further boreholes after comparing our results. So identify cavities and low velocity zone relatively weak. In these sections, we can see that if you found any low velocity zones in deep strata, then actually they can be treated in order to avoid further hazard in construction industry. Assessment of compaction, like for example, there is some really hard strata and we perform geophysical method, and then we found that there is also some weak zone. Then we need to perform compaction for those zones. And similarly, it is also required for, it is a criteria of universal building codes that we need to, or international building code, that we need to know the VS30 or VS100, like the upper 30 meter. We need to know the upper 30 meter layer VS velocity, like shear wave velocity, and the upper 100 meter shear wave velocity for site classifications. So the refraction is the first, which is actually STDM D5777 standard, and everyone has to perform method based on this standard. So in this standard, they have given some criteria. Based on those criteria, we actually perform the method, and then based on the P wave velocity, we actually derive bulk modulus, the shear modulus, and density of the soil or rock. and those values then we actually use for designing the structure. So seismic P waves are generated on the surface by an energy source such as simple sledgehammer or weight drop. The P wave propagates through the soil, rock, and when the seismic waves encounters interface between material of different seismic velocity, the wave then refracted according to Snell's law. So simple, we have just applied, like example, geophones. They are receivers, and when they, with the help of hammer, we produce some source, and when they are received, we actually acquire the knowledge. These refraction method has also applications like to understand the depth of the bedrock or subsurface structure faults, mapping geological strata, and repeatability and weathering of the rocks. So you may be aware of all these terminologies, like why we need to know the depth of the bedrock. I consider you an engineer, so you must know that you in any project you need to know the conditions of the site in order to further proceed with the constructions. Application of seismic refraction. Similarly, now how actually we are doing this, like for example, these are few boreholes, and then we perform the measurements, and then we compare all these measurements with some boreholes. So the functions for different types of hazards, we can actually perform a very simple test, and then we can detect our results. Like this subsurface fault here, they have marked a really good subsurface fault, which can be identified from the geophysical investigations. And in this layer, you can see that the depth rock is the depth of the bedrock is no more than 8 meters. Similarly, the mapping geological strata and reparability weather, these are also some few other comparisons which I have shown here. Is there any problem? Everyone can hear me, huh? Okay, so at the end, we actually present our data, and that data is actually in the form of the sections. We construct such sections, then we compare our result with the borehole, and then we present it to the client, and then he can decide what type of structure he can build. So for example, this is some data from refraction, and based on the result, you can see that for the upper layer, which is very soft, so normal excavation can be performed. But beneath that, normal or rock excavation he needs. So he can actually, according based on this survey, he can estimate his budgets, and he can cost the excavation, or he can plan based on these results. So these are the some result we actually when we provide, like for example, 40-meter distance or to the depth of like this, we can actually do normal excavation. Beneath that, we can do rock excavation or small linear excavation. So or beneath that, like from 7.3 meter beneath, there is rock excavation. So these are all results we actually present, and then according to them they decide what to do. So in 3D we can, like this is just a, like in 3D we can also present our results. These are the same result which we acquired in 2D form, but we have now compiled in 3D, and the whole site has been expressed in 3D form. Like here we can do normal excavation, here we have a normal or rock excavation, and here we have a rock excavation. Next method in the surface geophysical method is electrical resistivity. So electrical resistivity is actually a number of, I will just explain a simple what is electrical resistivity. And the resistivity measurement are made by passing an electric current into the ground using a pair of electrodes. And here we arrange two pair. These are two like these are 4 electrodes, so 2 are current electrodes and 2 are potential electrodes. We pass a current through the earth with current electrodes, and then the potential electrode measure the response. And based on that response, we actually got the resistivity of the soils or the subsurface rocks. And based on those resistivity, we actually distinguish the types of rocks or the character of the subsurface rock. So here is, for example, one example like geophysical techniques for imaging subsurface structure from electrical measurement made at the surface utilizing vertical electrical sounding and profiling. So these are the result of sounding, and this can be known as tomography. Sounding actually gives you one-dimensional result, but actually tomography gives you two-dimensional results. So what are the application of electrical resistivity? It is similar that I explained that in case of some seismic surveys, we can actually get the target is same, like for example, to identify the fault or fractures or cavities. Same with electrical resistivity, we can identify these features, but some methods can't be applied in some terrains or in some sites because they need special arrangement, they need special crew. So based on the simplicity, like which method is more simple, we apply those method according to the site. So electrical resistivity, when we apply, we can also get the result of the like if we need to identify if there is any fault or fracture zone in the site, or if there is what is the depth of overburden strata. So here this electrical resistivity also providing us the parameters are now different. In seismic, we were actually dealing with the velocities, and here in resistivity method, we are actually dealing with the resistivity of the soil or earth. So similarly, like this is a large zone, like very weak split zones we can identify, or these are the result of cavity. Like this is a cavity present after doing electrical resistivity, a cavity is being detected, and now this cavity will be treated accordingly. Same like for mostly in electrical resistivity method, there are a number of like profile arrangements, like survey arrangements. So mostly the dipole method is used for detecting cavities. Because dipole has very dense nature, and we arrange, like what do you mean by dipole? There are a number of array arrangements of electrical metal, like some are Schlumberger, Wenner. Like in electrical resistivity, if I say I want to use Wenner, then Wenner has its own function, like it can be used to detect water, and Schlumberger can be used to detect the like it has much depth penetration, but it actually it will miss some features. But dipole they are the such arrangement of electrodes that where there is no chance of missing any subsurface feature. Like the the data will be so dense that there is very less chance that we will miss any feature subsurface. So that's why for cavity detection we mostly use dipole array. And here, for example, you can see that an airfill cavity is detected, and when it is compared with borehole, it can be said that mostly it is found in mud rock like mudstone and gypsums. Similarly, these 2D can also be compared or can be compiled in 3Ds, and then we can show the whole map of the site that these are the weak zones, and these zones actually require some treatments. The next method is ground penetrating radar, ASTM D6432. This method is actually mostly used in detecting underground utilities and pipes, and mostly applied to concrete. In concrete, if you want to locate underground pipes or utilities. So this is actually electromagnetic properties. GPR actually detects the electromagnetic properties of the subsurface of Earth, in which we deal with the dielectric permittivity, conductivity, and magnetic permeability. These are the features. So GPR is like a method in which we have a transmitting antenna and receiver antenna. For example, there will be two in this four-wheel GPR system. You can see that inside there may be two antenna. One will be transmitting and the other will be receiving. And these are the some of the after the interpretation, we can say that here is some buried pipe, and you need to excavate. Rather than excavating a whole area, you just excavate the particular points. So ground penetrating radar consists of transducer and receivers, transmit electromagnetic impulse, energy reflected from various buried objects, and antenna receive the reflected waves, display them in real time on scan. So in GPR is like, if an experienced person is doing GPR survey, so it's really convenient and very easy that he can actually identify the buried utilities on spot, and he can just mark that there is some buried utilities, and then the next team will actually excavate and find the results. So similarly, the application of GPR is it can be further more applications like geology and hydrological investigation, engineering investigation to evaluate dams, sea walls, tunnels, pavements, road beds, railway embankments, piles, bridge decks, river score, building, and monuments. These are some of the applications like with the help of GPR, we can reduce our cost and can get like subsurface mapping for cables, pipes, and other buried structures prior to trench less operations. The next method is microgravity subsurface method. The microgravity method is mostly utilized in mining purposes, but here we can also find some subsurface changes, like we can find the weak zone or cavities based on this method. So microgravity survey is a valuable tool to characterize subsurface crust features. It can, because this methods, we can actually cover a large area, really big area. For example, 5 square kilometer or 10 square kilometer. So in this whole area, we can actually perform gravity survey, and then we can actually identify where the weak zone actually lies. So it can be utilized in urban areas where culture features and noise limit other technique like seismic and resistivity. Microgravity is the name that has been adopted for very high resolution gravity mapping. Microgravity survey are typically used to detect subsurface cavities or changes in subsurface density. Based on the subsurface density, like gravity, we will see like where are the dense rock, where are the less dense rock. When you create the whole map after gravity survey, then it will actually tells you the final result will be like where is the dense rock and where is the less dense rocks. So here is one map, for example, like after performing microgravity survey, here they have marked all the less dense rocks, and they can actually be interpreted as anomalies, change in the subsurface, and these changes are these changes are susceptible to collapse, or you can say that they are weak zones. Similarly, this is also some the applications of gravity, as I told you, mostly in mineral exploration, petroleum exploration, groundwater exploration, mapping geological structures and lithology, and in engineering projects. Engineering projects, mostly we are interested in identify the less dense rocks or less like more susceptible rocks that they are supposed to collapse or weak zones. So borehole geophysics method, why we need a borehole geophysics method? Boreholes, we actually, after drilling a borehole, for example, if there is a new project on island or in the inside the onshore, then we actually perform, instead of doing these long and tedious geophysical survey, we perform simple geophysical borehole surveys, and they can be like borehole seismic survey, borehole seismic tomographic survey, and borehole geophysical logging. So all these methods has different applications based on the need and desire. One can suggest like which method is more suitable, and which method will actually identify us the desired targets which we are looking for. For example, in some area, if you apply PS logging, PS suspension logging, and Yes, and there is no need for that. So it will be just like it will. You will you will know the shear strength properties of the soil. You will know the stiffness of the rocks or soil. But actually, you are more interested in the density or the other features of the, like if they are radioactive or they have other physical properties. So based on the desired physical properties, in simple, we can say that we can apply different uh, borehole geophysical methods. So the first is like the cross-hole seismic technique. In cross-hole seismic technique, we drill 3 holes in the earth, and then we apply 3 receivers, and then we produce some noise. And when these noise is recorded, then we can get compressional wave velocity and shear wave velocity. From this compressional and shear wave velocity, we can identify a number of parameters for the rocks, like their compactness, shear modulus, Poisson ratio, and many engineering geophysical parameters. So to explain the cross-hole seismic, the main purpose of cross-hole test is to acquire shear wave velocities, compressional wave velocities as a function of depth of engineering and environmental concern, which in turn can be used with the density to derive the dynamic soil properties. Yeah, dynamic soil properties, elastic modulus, shear modulus, and Poisson ratio. So these are the key parameters in predicting the response of soil and soil structure system to dynamic loading. A cross-hole seismic survey involves measurement of travel time of seismic energy transmitted between 2 or more boreholes in order to derive information on the elastic properties of the inverting material. One hole is used to deploy the source, and the other hole in other hole actually we deploy some receivers in order to record those noise. In order to obtain properties such as Poisson ratio, both P wave compressional and S wave shear data has to be acquired. This normally requires special source for P wave and S wave velocity. Waves are detecting using triaxial geophones clamped to the inside of the borehole using a hydraulic system. Data is collected at fixed interval to the hole, normally 1-2 meter. Like for example, here we see that first um, we deploy this to the surface, and when we lower the receivers with the interval of 1 meter, and we record the hole depth. For example, if this borehole is like 50 meter deep, then with the 1 meter interval, we can actually acquire 50 meter, 50 measurement, and based on those measurement, we will actually distinguish or characterize our borehole and the respective lithologies. So these are the standards. You can actually note down these standards and you can read them in order to understand. And whenever we perform such methods, we have to follow these standards. So the other tools are like, for example, cross holes. These are gamma logging. And these in gamma logging, we are actually borehole diameter and bulk density. We are interested in that. When we apply the gamma logging, we actually determine the bulk density of all the horizon. Vertical logging, vertical logging, this is now for oil and gas industry. For example, if you want to know the inclination of the well, like if it is inclined or if it is like exactly vertical, then you need to apply the vertical logging. Like this, you see R1, it will give you the result of inclination. Similarly, this suspension logging, is actually it's a big log, and it is lower into the borehole in order to find the compressional wave velocity and shear wave velocity. So we measure the P wave. Now this is a really complex method, and there are two. This is, you see, upper geophones, lower geophones. Now this upper geophones and lower geophones, it records actually 2 types of S wave. One we call far S wave and one we call near S wave velocity. Similarly, both these geophone also record the far P wave velocity and far near wave velocity. After recording those velocities, uh, we actually interpret the elastic moduli parameters of the subsurface rocks. So another method is a full waveform sonic logging, and we also measure in this method. We also measure the compressional wave velocity, shear wave velocity, surface wave velocity, and waveform. So these are applied to open hole water-filled borehole. Like the borehole should be filled with water. The downhole is like if you want to just test one single borehole, then rather than cross hole, you can just apply downhole methods. In downhole methods, um, if you have single borehole, so you can apply one geophones here. The geophone, it is different type of the downhole geophone is different than the normal geophone which we apply on surface measurements. And for this, this seismic wave is produced in three different types of it. First, you hit vertically, then you hit laterally, and then you hit horizontally. In three different types, you have to produce a waves, three kinds of waves. So it's more laborious work than technical. And then after that, you record some measurement, and based on those measurement, you can actually give the elastic properties of the soil. So these are some equipment which we use for the downholes, like seismograph. This seismograph we need for all the methods: surface seismic methods, if it is surface method, if it is reflection method, if it is refraction method, or if it is downhole or borehole seismic, we need to use the seismograph. And with seismograph, we need also the arrangement of geophones. Either it can be horizontally if you need to do surface seismic, or either it should be vertically if you need to do borehole seismic tests. So these are some results. For example, after doing a borehole seismic, you can see that we are actually getting two waves. One is VS, it is in meter per second, and one is VP. This VS is actually shear wave velocity, and VP is actually P wave compressional velocity. So based on the result, we can interpret our data, like for example, where the VS is increasing and where the VS is decreasing. And based on those VS and VP, we can actually, hello, we can actually identify the modulus and Poisson ratio of the subsurface rocks. So these are some of the presentation, like how we present our data to the client. So across hole seismic, these are the results after doing boreholes. A number of rays are generated, and then the final result is like the borehole section, which actually gives you the whole picture of the borehole. So these applications can be like the application of seismic borehole tomography can be like evaluating anomalous condition between two or more boreholes, such as sinkholes, sand channels, and other stratigraphic discontinuities. Evaluation of lateral and vertical material continuity. Chest data resolve hidden layer velocity anomalies that cannot be detected with conventional surface methods, and allows for final interpretation of standard cross-hole seismic. I will skip this method because this is just simple. Another comparison to the borehole seismic. This is actually parallel seismic test which we perform similar to the borehole seismic, but the method is different and we apply some different geometries. So now after borehole, we can study some borehole geophysical logging. So the first geophysical logging actually is the continuous recording of physical or chemical properties or parameters along or around a borehole by lowering probes inside the borehole and plotting the measurement as a function of depth. So the application of borehole geophysical logging, they are somehow like log top. You can use 3-arm clipper, natural gamma, fluid temperature, fluid resistivity, conductivity, or normal resistivity. These are the parameters which we use, and the application is the fracture, cavity identification, and lithological changes. Lithology and estimation of clay content in the rock indicates geothermal gradient and water flow in boreholes. Also, it indicates the water quality and salinity of the water. With the help of normal resistivity, we can find the lithology, fractures identification, and layer boundaries. So different log can actually provide you different types of result, and based on those results, you can actually interpret the data, and then you can go for the uh, final phase of the construction. Similarly, this is some other types of logging, in parallel flow meter, gamma logging, vertical logging, full wave sonic logging. So here you can also see now the applications are changing. Based on the type of log, the applications are different. Some are for cavity measurement and some are for clay content. So there is a big need of like one should develop a logging method that can actually provide all these result at once. But I actually it will be a really like then the interpretation will be really hard, and so that's why they have divided all the log in different phases, and then they can actually perform separate logging, and then they can detect the result individually. So in-situ density measurement we can do with gamma, a structural integrity of piles or detection of fracture zones. So these can be performed with gamma logging. Actual distance between boreholes, like vertical logging, and measure the borehole deviations, as I explained before. Full wave sonic logging, like lithological identification or rock strength and elasticity. The caustic televiewer is actually a new method these days when they lower the camera, high resolution camera inside the borehole, and then they actually take pictures, and then based on those pictures they interpret the like if the rock is really fractured, like uh, they like alternate to all these logging. This is new method is a caustic televiewer when they lower the high resolution camera, and actually they record the whole borehole up to a depth of 50 meters, 60 meter, and then they actually visualize every all borehole in some section 1 by 1 meter, and then you can actually see like it can be presentable to you like you are looking at a wall, and you can see the cracks and all the voids in that borehole. So you can also interpret like that. So this is some boreholes. After like doing all these loggings, you have to compare with your result with the borehole, because without comparisons, these records are not acceptable. So always you have to compare your geophysical data with the borehole records. So they are actually recorded, like for example, subvertical joint in this section. It is confirmed by the borehole that this is a subvertical joints. And when you apply the geophysical to whole area, so this subvertical joint should appear in your geophysical results. And if they are extended somehow to other directions, you can also interpret them. The last thing is marine geophysical method. So marine geophysical method is the like when you apply to a method. These methods are how we apply the marine electrical resistivity tomography, sub-bottom profile survey, side scan sonar survey, and marine magnetometer survey. So this is similar to electrical resistivity method, and the applications are like include characterizing sediment types, sand versus clay, and mapping geological structure, detect the thickness of the upper consolidated layers. Actually, in order to understand all these methods in detail, one have to, now this is actually introduction to all these methods. So I cannot explain like all these methods in detail, how we actually apply all these methods on surface, how we arrange our electrodes, and how we acquire the data, what type of parameters we need to set to acquire all those data. So when somehow when we like explain these method one by one, then it will be really easy to understand. So just in simple, you can understand that for marine electrical resistivity tomography, we are applying the electric resistivity method in order to characterize the sediment types and mapping geological structure, detect the thickness of the upper consolidated layers. So this gives an indication of lithological and structural variations of the subsoil, since resistivity depends on the type of material, porosity, density, and conductivity. Based on these three parameters, we actually detect these three parameters from our result, and based on these three parameters, we actually interpret the subsurface results. So the instrument here used is, for example, there are a number of instruments like Superstring, Siskel Pro, Geometive. These are the name of the instrument, but the basic concept is same. You have to pass the electric current through the earth, and you have to record the resistance of the earth. Some of the instruments are very rigid, very complex, like they require a lot of time. Some are very user friendly, and you can actually deploy very quickly and get the result, because these surveys are not just like matters of hour. It takes days, sometimes it takes weeks in order to complete all these surveys. So this is just an example of one instrument that is used for marine geophysical survey, and it is Superstring, known as, it has GPS and also temperature sensors it can record. So it is, for example, this is the result of marine electrical resistivity tomography. So you can see that this, based on the interpretation, we can see that the blue section is actually the depth of the seabed, and the seabed is like depth 4 meter and 6 meter. So usually it is required when you want to construct some buildings on the seabed, then you need to know the depth of the seabed in order to perform the constructions. Similarly, some other result, like this is the seabed, which is actually the depth is also like 3 meters. Somehow it is varying from 3 meter to 6 meter. And this is the upper soft lithology, and this is the rock interface. So you can actually perform these method too. Similarly, you can present our data in different form, and you can actually define the rock strength and rock distribution throughout the area. These are the multi-beam echo sounder. Now, what is multi-beam echo sounder and why we use this? Now, this echo sounder is actually used to determine the pipes and like the buried pipes under this on the seabed. And we can actually, it's simple like a drone survey. When you perform some drone survey, and then you create a mesh, and then you combine all the data, and then you interpret the result, and then you can say that these are our buried pipes, which are actually in the sea. So this some other result of the multi-beam echo sounder, like you can see that you can find the trench walls, pipe in the trenches, and actually pipe and trench. So these are the pipe, either it can be gas pipe, petroleum pipe, or even other pipe. You can actually detect with that. So the other method is sub-bottom profile. Sub-bottom profile, like when we are unable to perform marine electrical resistivity, or to find the depth of the bedrock, sea bedrock, then we actually apply sub-bottom profile survey. This sub-bottom profile survey actually identify and measure various marine sediment layer that exist below the seabeds. Acoustic source generating signal will be reflected from the boundaries that have different in acoustic impedance. And to map the thickness of the upper unconsolidated layer along of all pipeline routes, the contractor can specify the types and capacity of the dragger that will be used to excavate. I think there was some problem. So this is the result of the sub-bottom profile survey, like measure thickness of the sediment layer or depth to the top of rock, study submerged structures such as pipeline cables, dams, bridge, footings, etc., and useful in dragging and constructions. So these are another result of interpretation. Like you can see that this is a seabed depression. We can also interpret the seabed depression and seabed multiple. Like these are the multiple layers of the seabed. And the final result is like this. We can present to the client that the seabed is like this. There is one depression, and the first layer is like up to such depth, and the second layer is to such depth, and third layer is up to such depth. Also, we can actually show our results in order to map the whole area, like where the hard rock, like here the hard rock occurs from 0.5 to 3 meter, where here it occurs from 0 to 3 meter depth. So these are the distribution of the rock with depth less than 3 meter from seafloor, and the other rock with depth more than 3 meter from seafloor. So side scan sonar survey. This is similar to sonar survey, but actually the technique is different, and we apply the side scan in order to identify the same features. Like we can identify pipelines, buried pipelines, or the seabed mount or cables actually. So these are the result, like we present our result in here. Like for example, if there is any depression in the seabed, then we can actually give us the lat long after, like if it is debris rock, it is on such locations, and then we can present. So marine magnetic survey is similar. Marine magnetic record the spatial variation in Earth magnetic field. In marine magnetic survey are often used to detect the composition of magnetic material found on and below the seafloor. Every kind of material has unique magnetic properties, and different materials below the ground can cause local disturbance in the Earth magnetic field that are detectable with sensitivity magnetometers. So marine magnetometer can either be stored at the surface or near to the bottom. In both cases, a significant distance away from the ship to avoid pollution from the ship magnetic properties. So here it is stored behind the ship, but mostly we are actually taking this to the depth in order to keep it away from the ship. So these are actually good in detecting ferrous objects, like if there is any, for example, it has application in militaries. They are actually trying to find if there is any mines or something inside the earth, so they use the magnetic method. So this is some result, like whenever you apply, you will find such anomaly, like a change or spike in the data, then you can say that this is our magnetic anomaly. So these are the whole map of the area. For example, after doing detailed magnetic survey, we can say this is pipeline marker, or the pipeline is actually going in this way. So you can follow all these methods based on the geophysical survey. Some of them have similar application but different methods, and some of them have different applications, and we can apply all these methods in order to achieve our targets. So thank you all for listening patiently.